The last topic that we need to talk about with respect to stoichiometry is limiting and excess reactants, and this is going to lead us to one extra little blip about percentage yield. Now, when we look at a chemical equation, we like to think that it tells us everything we need to know about a chemical reaction, but unfortunately, it doesn't tell us the whole story. There's lots of information that would be useful to us as scientists, but that isn't written down, such as the exact conditions that you need for the reaction to happen. For example, there's some reactions that require a certain temperature, some require stirring. For some reactions involving gases, they need to be under pressure. The behavior of the atoms during the reaction, how they actually rearrange. This is a major topic looking at reaction mechanisms out of Chemistry 12. And the nature of the reaction, whether or not that reaction happens quickly or slowly. Again, a topic out of Chemistry 12, which looks at reaction kinetics. In the real world, although we like to imagine that all reactions go 100%, unfortunately they don't. And that's because not all molecules have enough kinetic energy to react. What we know kinetic energy is a measure of speed. If reactions are, or reactants rather, aren't moving fast enough, they aren't able to overcome the repulsion between the molecules, breaking the bonds and therefore allowing the atoms to rearrange. So, as a result, not all reactions actually happen to the extent that you would like them to. So in order to get more of the reaction to happen, in other words, we're going to use the most ideal conditions possible, we add an excess of one of the reactants to the reaction. And this particular reactant we'll call the excess reactant. When you go about choosing, well, which reactant should I make the excess reaction, there's a couple of things that are quite intuitive to think about. One, which one is cheaper? If you are reacting gold and hydrogen gas, it probably makes a lot of sense that the hydrogen gas is cheaper than the gold, so you would want to have that in excess. Similarly, for that particular example, you'd want to choose the one that is most abundant, the easiest one to get a hold of, hydrogen gas to have as the excess. Also, we want to consider which one will be the easiest to get rid of after the reaction is done. So if I have a reaction between a solid and a liquid, and my product is a solid, it makes sense to have the liquid being in excess so that I can simply filter my product after the reaction is done. Now, if one reactant is in excess, then the other one we call limiting. Looking at the example up at the top, I have 8 car bodies and 48 tires. The question is, which one limits how many cars you can build? Well, the car body. And going back to what we just said, well, how would you choose which one you want to have excess? Well, it makes a lot of sense that it's cheaper to have extra tires kicking around, and 2, it's a lot easier to get rid of extra tires than it is to get rid of extra car bodies. So the limiting reactant happens to be the one that gets used up first in the reaction. And it determines the amount of product that you produce. When we looked at the car body example, how many cars could you make? Well, the car bodies were used up first, so that stopped using the tires. And because we only had 8 car bodies, it was only possible to make 8 cars. So in stoichiometric calculations, we can find the limiting and excess reactant in either units of moles or grams. And what I say is that when you're given numbers for 2 reactants, you're going to arbitrarily choose one to predict or calculate the other. So the example we're going to look at is the reaction between zinc and hydrochloric acid, and we have 1.21 moles of zinc and 2.65 moles of hydrochloric acid. Now the question is, which one is in excess and by how many moles? Well, the first step in stoichiometry is always having a balanced chemical equation. And the balanced chemical equation for this particular reaction looks like this. You have zinc and 2 hydrochloric acids producing zinc chloride. Notice that zinc is a 2 plus ion, chloride a 1 minus ion, so when they pair together you need to have 2 of the chlorides, and hydrogen gas being a diatomic. Now you're going to choose one of the numbers that you're given And using the mole ratio from the balanced chemical equation, we're going to calculate the other one that you would theoretically need in order to react all of the one that you chose. So I have 1.21 moles of zinc, and I'm going to calculate how much hydrochloric acid it would require, even though I know that I have 2.65 moles. So if all the zinc is reacted, and I started with 1.21 moles, I have 1.21 moles of zinc, and I'm going to use that one to calculate the other. So I'm going to pretend like I don't know that number for right now. So to calculate it, I need to draw an X and a line. The unit that I have goes on the bottom. So moles of zinc goes on the bottom. The unit I'm going to goes on the top. Moles of HCl go on the top. When I go side to side in my diagram, I use the coefficients from the balanced chemical equation. Remember, that's the only time you use those coefficients. So a 2 is going to go in front of the HCl, and a 1 is going to go in front of the zinc, which means that if I reacted all the 1.21 moles of zinc, it would take 2.42 moles of hydrochloric acid. So we only need 2.42 moles of HCl, but we have 2.65. Because I have more than I need, the HCl is in excess, and by 0.23 moles. Because it's in excess, that means that the zinc is the limiting reactant. And as soon as you find that out, I'm going to suggest you throw a star beside it, because once you know it's the limiting reactant, every other amount gets calculated from that number. So the moles of product is found by using the moles of the limiting reactant and the appropriate mole ratio. So I have zinc, and I still had the 1.21 moles of zinc. I'm going to draw an X and a line to change the units. I want to put the moles of product. The first product I'm going to look at is zinc chloride, and the moles of zinc on the bottom. What we see here is that it's a 1-to-1 relationship, which means I would need 1.21 moles, or make 1.21 moles of zinc chloride. I could do the same calculation to calculate the amount of hydrogen gas that I can make. Again, I start with the amount of my limiting reactant, my zinc. I draw an X and a line to change the unit. The mole unit goes on the bottom, and that's moles of zinc. The mole unit going side to side that I'm calculating goes on the top, moles of hydrogen. Like I said to you last day, when we look at the units, we can only change one of the two numbers at a time. I can either change the moles of the mole to a gram, or I can change the identity, the hydrogen to the zinc. When I compare moles to moles, I use my coefficients from my balanced chemical equation. And again, this time it happens to be a 1-to-1 relationship. So I get 1.21 moles of hydrogen gas as well. Now the same procedure can be used to find the limiting and excess reactant when the amounts given are in grams instead of moles. However, when you calculate the excess reactant, you still have to compare moles to moles or grams to grams. So for our next example, what we're going to look at is having 10 grams of zinc react with 10 grams of hydrochloric acid. And the question becomes, well, which reactant is in excess and how much hydrogen gas will be produced? The first step is always to figure out what your limiting reactant is. And what I suggested to you before is that you take one of the numbers and you use it to calculate the other. So in this particular example, we're going to say that we've got 10 grams of zinc, and although I know that it gives you that there's 10 grams of hydrochloric acid in the question, really I'm going to throw a question mark behind that. That's what I'm going to try and find out first. When I say I'm going to try and find that out, I'm going to say try and find out, do I need all of that 10 grams or do I need more than the 10 grams? So I set up my little flow chart, and like you've been doing before, I know that if I have 10 grams of zinc, that's always my starting point. When I hit an arrow, I draw an X and a line, and the unit that I'm going from, grams, goes on the bottom. This is grams of zinc. The unit that I'm going to goes on the top, in this case, moles of zinc. Now, when you have moles and grams together, don't forget you always use a 1 in front of the mole. And for zinc, the molar mass is 65.39. That came from my periodic table. Now on my chart, I'm way down here at the mole. So again, I hit another arrow, which means I have another X and another line. Now, looking at that arrow, I know that I have moles of zinc that I'm going from. That from unit goes on the bottom. The moles that I'm going to are moles of HCl. And looking at my balanced chemical equation, because I've got moles and moles together, I see that there's a 2 in front of my HCl and a 1 in front of my zinc. The very last step is because now I'm over here. I've got another arrow, so another X and a line. And this time I'm going to go from moles of HCl to grams of HCl. When I have grams and moles together, a 1 always goes in front of the mole. And for HCl, its molar mass is 36.46. Because I've hit the destination, the point that I was trying to have or calculate, I put an equal sign. And now I just put it in the calculator. So 10 divided by 65.39 times by 2 and and multiply by 36.46. And that gives us 11.15 grams. Now, that's how much HCl I would need in order to react all the zinc. The question I have for you is, do you have that much? I would need 11.15 grams, but I only have 10, which means that the HCl is my limiting reactant. And once I know it's that limiting reactant, I will determine every other number from that. Although I have the flow chart set up for you to figure out how much hydrogen gas there is, I'm going to leave that for you, and we'll work through this particular calculation next day in class.